Thank you very much. Good morning from my side as well. As said, I'm Johannes Mersch from Johannes Kepler University in Linz, currently doing a postdoc fellowship sponsored by the Austrian Academy of Sciences. Before going into the electrical impedance tomography and the grid-based soft sensing, I want to do a quick diversion for the motivation. So as we've already seen, if you put in conductive particles into a matrix, or today I'm mostly talking about elastomers, most prominently PDMS or silicones. If it's carbon black or carbon nanotubes or graphene, doesn't really matter. You can get to a conductive system if you surpass the percolation threshold. And if you tune your material to be in that percolation area, for strain sensors, you can get to very, very high gauge factors or sensitivities, which make these materials very promising for a number of applications, ranging from wearable devices, soft robotics, but also for actuators themselves, such in dielectric elastomer actuators. Now, if you look at such a material, this is a commercially available silicone carbon black yarn, stretches to over 100%, very low resistivity for at least carbon black loaded systems. And if you then characterize the system, you can see the response is very linear. This is quasi-static, so slow deformations. The problem is the elastomers are viscoelastic, have viscoelastic properties, meaning that depending on your strain rate, the stress changes. And there we can see a very interesting phenomenon that if you strain the material, then keep the strain and relax it again, in the force signal, you can see this relaxation, right? So you get to the first peak, you have relaxation, goes back. But the resistance increases as expected, drops a little bit due to the relaxation, but you get a secondary peak. And in the electroactive polymer community, this was coined by Ian Anderson as the bunny ear phenomenon, but it's also known as, for example, the shoulder phenomenon, because you get the primary peak and then kind of a shoulder if you do cyclic testing. And depending on strain amplitude, you even get like a secondary peak at 0% strain, or at, let's say, your lowest strain level in a cyclic application. And the material can show all these phenomena in at different strain levels. So we assume that the underlying phenomenon is the same for the shoulder phenomenon, high secondary peak, low secondary peak, and this bunny ear. We developed a equivalent circuit model. So these are not experimental curves, but simulated curves, which can emulate this behavior. And we can, for example, if we change the viscoelastic properties, see that we also get this conversion between the lower secondary peak to nearly a monotonic shoulder phenomenon. And this model is based on the percolation, the viscoelasticity, and the transversal contraction, because we assume that this phenomenon is based on different time constants, basically, of longitudinal and transversal contraction. And besides the long vision of having large area, very stretchable, very compliant sensors, that's why having a distributed sensing allows us also to better characterize these phenomena. Now, there's different approaches to this. You can have distributed sensors, EIT, so electrical impedance tomography, or grid-based sensors. And I just show you a first approach of what we did with grid-based and electrical impedance tomography sensors based on these stretchable carbon black silicone materials. For the grid-based sensor, we opted for very conductive textile electrodes. This is a silver-based conductive knit, very stretchable, so we don't really interfere with the stretchability, and this can easily stretch to 30 or more %. It's all encapsulated in a non-conductive matrix, and we have an 8x8 grid sensor. The grid-based approach has the advantage that in comparison to single sensor nodes, the number of electrodes or connections scales by m plus n instead of m times n if you go for large areas sensors. And yeah, so we put that as well in the tensile testing machine and strained it to various strain rates. The same with the electrical impedance tomography setup, where we have the electrodes on the outside, also very stretchable conductive nit, and the conductive elastomer in the center as the device under test. Now, we use for both measurements a SIOSPEC, which is actually an electrical impedance spectrometer, but which has an EIT mode. Then we did use an adjacent current injection pattern, which is standard, and did the reconstruction IDOS, assuming or using a Lagrange prior, because we assume that the resistivity doesn't change too much. Now for the EIT reconstruction results, you can see very nicely that with increasing strain, so this is 20%, we're starting to see certain resistance change. And for 30%, we can see what we assumed to see, that due to the transversal contraction, the resistance change is not homogeneous. The grid-based sensor allows for a lower resolution, just because we have just 8x8 grid. The resistance change is in a similar order of magnitude, but we don't see this this transversal contraction. This is likely because we have crosstalk between the electrodes, and we're working on how to improve that and overcome that problem. So for the conclusion, we have some advantages of the EIT, which is that we have a quasi-continuous resistance distribution, and we just need a small number of electrodes. The problem or challenges that we're having is, first, it's very susceptible to artifacts, so it matters a lot how we are doing the reconstruction, which parameters are we using. And what we haven't considered in this study presented here is the electrode movement. So in literature, there's been many sensors, for example, force measurement, like touch sensing, which use EIT, but there the electrodes don't move. In our system, if we go to 50%, 100% strain, the electrode movement is quite significant. And we have to take that into account to not confuse resistivity change and just geometry change. For the grid-based, that's where the grid-based has some advantages. We're not making any assumptions about the system, so we don't have to do reconstruction. So it's basically a simpler setup. And if we go into, for example, the zero potential circuit method, we can get to lower crosstalks and also very, very fast measurement cycles, which is important for the dynamic phenomena we're trying to capture here. The disadvantage is that we get a lower resolution, but depends on the number of electrodes, basically. And we have to eliminate the crosstalk. That's also what we want to research next, is minimizing this crosstalk and using more specialized electronics instead of the commercially available SIOSPEC system. So with that, thank you very much, and open to any questions.